So now we want to look at and explore a horizontal asymptote. We've looked at being able to have discontinuity with a domain, and that would then describe our vertical asymptote and our holes, if we have any. We've looked at what does the graph of a rational function even look like, and when we did that, we noticed that not only does it have this restriction of an x value, meaning a hole or a vertical asymptote, but it also had a restriction of the y value, which we saw a horizontal asymptote. So when we look at a horizontal asymptote, let's see what it could kind of look like. So we really have kind of three scenarios when we look at a horizontal asymptote. The first scenario that we see is that we do not have a horizontal asymptote. Instead of a horizontal asymptote, we have something that's called a slant asymptote. A slant asymptote is also called oblique asymptote. Okay. So the first scenario is going to be no horizontal asymptote because instead it is slanted. The second scenario that we might have is that our horizontal asymptote is at 0, which having the horizontal asymptote at y equals 0 just basically means it's the x-axis. So if I see that the graph is approaching the x-axis, we'll say, okay, well, it's at y equals 0. And then we could also have another scenario where we have a horizontal asymptote that has been shifted off of the x-axis to some number here. So this is just going to represent some y value, all right? So we see that in the third case there, where our horizontal asymptote is actually at 2. So if I look at this first graph here, for our purposes, we would just say that there is no horizontal asymptote, and I'm just abbreviating horizontal asymptote as HA. In the next one, we notice that the graph itself is approaching that x-axis. Therefore, we would have a horizontal asymptote at y equals 0. On our next graph, and here's the thing, they don't have to be nice enough to draw the dashed line. Like in the last one, they didn't draw one on top of the x-axis. So I might not actually see this dashed line, but since I do, I can see that that dashed line is going through the number 2. Or I could also look at the graph and see that it's approaching, it's leveling off at the y value of 2. So this one would have a horizontal asymptote at y equals 2. Right? So graphically, I can look at them and tell kind of what's going on here. If instead I had an equation, then what I'm going to want to do is I'm going to want to compare the highest exponents of the numerator and the denominator. Remember that when we first started looking at a rational function, we said a rational function has polynomial functions on the top and polynomial function on the bottom in the denominator. So remember, if we think back to a polynomial function can be described by that leading coefficient. So since the polynomial function that is actually part of this rational function, if it can be described by the leading coefficient, then so can the rational function, all right? So the rational function can be described when we're looking at the horizontal asymptote by its leading coefficient. So remember that leading coefficient test, we looked at the numerator's highest exponent, and then we looked at that denominator's highest exponent, okay? Now, when we look at the highest exponent, if we've got two numbers, there's 3 ways to compare those two numbers. I either have the top being bigger than the bottom being bigger than the top, or they are equal. So those are actually the 3 scenarios that we have, all right? And this is just kind of, I have to memorize those 3 scenarios. So what it might look like, let's see an example here. Let's say we have the function 5x plus 7 over 2x minus 4. All right, so when I look at this equation and I want to find the horizontal asymptote, what I'm going to do is I'm going to compare these highest exponents. So when I look at this highest exponent here, and here I notice that they are both a 1, right? No number means there's a 1. So since the numerator highest exponent and the denominator highest exponent are both 1, they are equal, that means that I will have a horizontal asymptote at y equals a over b. So then the question is, well, what is a over b? Remember, a is going to be the coefficient in front, and b is going to be my coefficient in front. So my horizontal asymptote for this function would be y equals, y equals 5 divided by 2. And you can just leave it as that fraction. If you want to write it as 2.5, you can do that as well. All right? So since they were equal, I took their leading coefficients and I divided them. Okay, let's look at another example. Let's say we have the function x squared minus 9 over x plus 7. All right, so now what I'm going to do, again, I'm going to look at my highest exponents. And remember, since there's no number on the bottom, it's a 1. So my numerator exponent is a 2. My denominator exponent is a 1. So therefore, my numerator exponent is greater than my denominator exponent, which means that I have no horizontal asymptote. So there could be a slant or oblique asymptote, but right now we're just going to pause and say, okay, there's no horizontal asymptote. Okay. Now, let's look at one more so we can see our last scenario. Let's say we have x plus 5 over x squared minus 16. So if I'm trying to find the horizontal asymptote here, I'm going to look at the highest exponents, all right? Again, since there's no number on the top, it would be a 1. So my numerator exponent is a 1. My denominator exponent is a 2. So this time my numerator is less than my denominator exponent. Therefore, my horizontal asymptote will be at y equals 0. Okay, so now I should be able to, from an equation, I've memorized those 3 scenarios, so I should be able to compare the highest exponents and place them in one of those 3 categories of horizontal asymptotes. I should be able to also look at a graph and determine which of those scenarios I have as well.